So up until this point, we've been using integration by parts on indefinite integrals, and I just want to go over an example of using it on a definite integral, which it's not much different than any other definite integral, except there's just like this extra set of terms when you from this uv that you have to worry about. So let's try the integral from 0 to 1/2 of the function x cosine of pi times x dx. So see, we have our limits here. Okay, and can we do u substitution? Let's think about this real quick. X being u, no, that's not going to happen. X being cosine of pi x, or sorry, u being cosine of pi x, is that going to help us? No, we're just going to differentiate and get signs, and that doesn't help us at all. So quickly, we've ruled out u substitution. We're going to do integration by parts. And what we want to do is select our u to be the function that disappears if we can. And I want to be clear that you will not always run into a situation where you have an algebraic function as one of your functions that will decrease in power as you differentiate. There are more complicated examples of integration by parts problems where that doesn't necessarily happen. But when you do have something like that, something like an x or an x squared even, or some higher degree, usually, not always, but usually you want to choose that as your u, especially when it's paired with something cyclical like a cosine or a sine or some trig function like that. Okay, so let's let u equal x, and let's let dv be our everything else, right? If u's x, everything else has to be dv. So that would be cosine of pi times x dx. So then du is simply dx. dv, when you integrate it, gives you v. And when you integrate cosine of pi, right, so we want to integrate this. When you integrate cosine of pi x, well, that's sine of pi x over pi. If you've been watching these videos, you should know why that is. And so let's move on quickly to the next part of this problem. So we see that the integral from 0 to 1/2 of x cosine of pi x dx is equal to, now this is where you're going to see something just slightly different now that we have limits put in place. We do our u times v. So right, this is x sine of pi x over pi. But here we have to note that we need to also apply the limits to this function here on the left side. So we have to do this from 0 to 1/2. And you'll usually see it written as like a bar, just showing, look, you want to take this function from 0 to 1/2. You use the same sort of method you use when you solve definite integrals, where you plug in the upper limit and you subtract from it the lower limit. Okay, and then you can do that virtually at any time. I'm going to not do it right now. I'm going to solve this integral and then kind of do everything all together. But you could sort of do this part, figure it out right now, and then you'll have whatever belongs on the left. But I'm going to save that and do it in like one fell swoop. So I need in my integral v du. Well, here v is, it's sine of pi x over pi. I'm bringing that over pi out front as 1 over pi. And then we have sine of pi x times d times our du. Well, du is just simply dx. Okay, now when we do this, we get, I'm going to do something. I'm going to note that here I have 1 over pi, and here I also have 1 over pi. I'm going to factor out a 1 over pi because it's just no point in continuing to write that in both terms. And that's going to be multiplied by x times sine of pi x, taking at these limits, minus this integral here. So let's think about this, the integral of sine of pi x. Well, it has to be negative cosine of pi x over pi, right? has to be negative cosine because the derivative of cosine is negative sine, but we have a positive sign, so we need to take negative cosine. And then this whole thing needs to go from 0 to 1/2 as well. Okay. Now we can start cleaning things up. And note also that the whole entire thing is together can be taken to this one, these two limits at the same time. So two boundaries at the same time. So we could rewrite this as x sine of pi x minus negative cosine is plus cosine of pi x over pi. And note I can't factor out this pi because there's no pi here. So if I factor it out, I'm going to have to put a pi out front. And why would I do that? It just doesn't make sense to add more constants. So this whole entire thing, I need to take it to these, apply these boundaries. Okay, so now we're going to get our 1 over pi out front. And then we have to plug in this upper boundary everywhere first. And then subtract from that what we get when we plug in the lower boundary. So we have x is 1/2 sine, and I almost forgot my x up here. 1/2 sine of pi times x. Well, that's pi over 1/2, or pi, times 1/2. That gives you pi over 2. Okay, plus this is cosine of pi over 2 for that same reason, divided by pi. And then we need to subtract from that what we get when we plug in our lower bound. So we get 0 times sine of pi times 0, right? Plus cosine of pi times 0 over pi. And we have to try to fit those brackets there. And then what do we get? So we got some simplification that we can do here. So I still have this 1 over pi out front. Let's see, can any of this go away? Well, cosine of pi over 2, it's 0. 0 over pi is 0. Great, that goes away. 0 times sine of 0, both the 0 and the sine of 0, that's all 0, so that goes away. So now, oh, by the way, sine of pi over 2, that's easy. That's 1. So what we end up here with is 1/2 times 1. Well, it's just 1/2. Plus, well, cosine, that all goes away. And then we get minus. So actually, we're not going to have plus anything. We get minus, right? And this is a positive cosine, so the whole thing becomes minus. And we get cosine of 0, because pi times 0, that's just 0. So cosine of 0 is 1 over pi. So we get 1 over pi. Okay, we can, I'm just going to write it real quickly here, that this is 1 over pi, and then I'm combining my fractions here. Just doing some cross multiplication, I see that that's pi minus 2 at the top over 2 pi, the denominator. And we see that we get, distributed in the pi, we get that this is equal to pi minus 2 over 2 pi squared. And that is our answer.